Hello, everybody. It's great to be back here with everybody. We're up on a proper stage this time, so I have to be very careful not to take a dive. Every speaker, pay attention. So I want to get us warmed up first before diving into anything too technical, too difficult. So I'm going to start by teaching you just something fun and that I find fun and interesting. And then I do think he's going to be able to draw some lessons back into what we do as programmers. And I brought some props. Yes, okay. I've got my cubes. So, the Rubik's Cube is one of the best-selling toys in history. It's almost 50 years old now, but it's basically more popular than ever. I took this photo right here in Madrid, just happened to be, I was already planning to talk about Rubik's Cubes, but right there on the street, walking around, a whole shop full of them in one of the little markets. The original patent on the cube expired like in around 2000 or something like that. And so now there's this whole diversity of really innovative companies making really nice cubes and all variations and really nice things like that. I think part of the appeal of the cube is that it is unreasonably difficult. If you set out to make a puzzle, you probably wouldn't make it that hard. Its inventor, Rubik Erno, wasn't really trying to make a puzzle. He was trying to explore mechanisms that could move independently in different directions without falling apart. And it wasn't until he messed up his experimental mechanism and then tried to straighten it back out again that he realized it was hard. And it was really hard. And as the story goes, everybody at the academy in Budapest where he worked, they all got hooked on trying to solve this puzzle, trying to put it back together. And it took a full month before the first person succeeded. So it's hard because there's so many states, right? There's so many different combinations. And if we were to try to count them, so there are 8 corners on a cube. And so if you took them all out and you put them back in a random order, you'd have 8 choices for the first one, 7 for the next, times 6 for the next. So that's 8 factorial kinds of combinations. Oh, see, you didn't know there was going to be math. Sorry about that. Now, each corner can be rotated 3 different ways. So we've got another 3 to the 8th factor there. Then we've got our 12 edge pieces, which get permuted. And all the edge pieces have 2 different orientations. So we're up to a pretty big number here. This is the number of cubes you can get if you take it all apart and put it back together in a random way. Now, thankfully, that's not all. You can't possibly do all of those combinations when you're just solving the cube, because when you make a turn on the cube, you're never moving one piece at a time. So there's certain invariants to the puzzle. One of them is that if you count up how many swaps of pieces have to happen to solve the puzzle, that's always an even number of swaps. There's never an odd one. You can't do that without breaking the puzzle and putting it back together. So that cuts our search space in half. And there's a similar thing that goes on with the corners. The number of corner rotations needed is always divisible by 3. So all the corner rotations that are not divisible by 3 don't count. And finally, all the edge flips. There's always an even number of edge flips as well. So that cuts down our search space, and it gives us our total size of how many different Rubik's Cubes there can be. And it's 4 times 10 to the 19, which if you stacked 1 cube for each of those, it would be 256 light years tall. So it's a pretty big search space. And that's why I want to draw the first connection back to programming, because the space of possible cubes is very big and very alien to our experience as human beings. But so is the space of possible programs that we can write. In fact, that space is bigger and weirder than the space of cubes. And in both cases, you're a person who's trying to navigate this vastly alien space of possibilities to get to a very specific target. So I think it's interesting to analyze how is it that we, both as programmers and as cubers, can actually do that. So how do people do it? Well, people can solve the cube really fast. Recently, this gentleman, Yiheng Wang of China, broke the world record for the fastest average time on a 3x3x3 cube. He's 9 years old. His average time was 4.48 seconds in the event. That's what you get scored on. And this particular solve was 3.95 seconds. So he gets 15 seconds of inspection time. He has to put it down, use the electronic timer, and boom. He's a real prodigy. Really took the cubing world by storm. I shudder to think how fast he'll be in a few more years if he keeps at it. But his result's just the latest in a long string of stunning improvements in a very intensely competitive field of speed cubing. The world record keeps falling. Cubers today, the top ones, the best in the world, are like twice as fast as they were a decade ago and 4 times as fast as they were 2 decades ago. Some of that, I think, is because the cubes have gotten really good, and I brought my props specifically, so you should totally come up after and find me and get to play with them, because if you ever played with the old Rubik's Cubes, they were kind of stiff and slow and hard, and these are very, very fast and fun. I think that's a piece of it, but I also think one of the reasons people are getting better so quickly is that the rise of YouTube and TikTok have really allowed a global culture of people interested in this one niche challenge to share techniques, learn faster, innovate, and then share those innovations back with the community. So all of that has really caused an explosion in technique and speed. So let's break down what people actually do when they solve the cube. So yeah, there's going to be more math. We're going to make a little graph here, and we're measuring on the bottom axis how many turns you have to do to solve the puzzle. And on the top, we're going to measure how much of the puzzle is not solved yet. And instead of repeating those really huge ungainly numbers like 4 times 10 to the 19 possible states, I've converted them into bits. And because what that really means is we've got an unsolved cube has about 65 bits worth of randomness, which when you think about how much you can do with a 64-bit number is a lot of stuff. So an unsolved cube is 65. If you go and follow a beginner tutorial on how to solve the cube, it'll probably teach you to start by forming a cross of one color. It usually tells you white, and that's your first step. And then it's going to tell you to finish the rest of the layer. It's going to teach you the steps for that. And then it's going to have you move on to the second layer, which is another 4 edges. And you can see on my graph that our unsolved bits is coming down. We're already down to something like 18 bits at this point, but we spent about 60-something moves to get there. Then you're going to orient the edges on the top. You're going to permute the edges on the top to get in the right places. You're going to permute the corners, orient the corners, and then you've solved the cube. And it's about 100 moves to do it with the beginner method like this. And if you practice, you can learn to do this pretty fast. People can even do this relatively quickly, because if you spin fast enough, even 100 moves doesn't take too long. But Yi-Hang Wang's not using this method. The fast speed cubers, they start the same way. So I'm going to use a different color here, blue, for what a more advanced speed cuber is going to do. They still start with the same first state. They still form that cross. The main difference is they're usually going to make it at the bottom because they don't really need to see it, and they'd rather have their eyes on all the other parts that are not solved yet. Which cross will they make? Well, in principle, you could pick any color to start with, and so you might imagine that really good cubers are going to just choose all the colors equally because they're going to find the very best one. And surprisingly, that doesn't happen that much. Some people really are color neutral, but it's really hard to become color neutral, like fully color neutral, where you can pick any color. So Yi-Hang actually mostly solves on white and yellow only. So it's interesting when you think about the psychological trade-offs. That's the stuff that I keep finding fascinating and connecting back to the other kinds of work we do, because we are also trying to pattern match and decide where to invest our effort. Do you get really, really good at 2 colors, or do you spread that effort out across 6 colors? It's an interesting trade-off. So anyway, once they've solved the cross, though, the advanced solvers go directly into solving both layers, the first and second layers together. First 2 layers, F2L is usually what it's called. And this step is generally considered the hardest part of solving the puzzle because there's still too much complexity to do anything rote or completely memorized, right? And you can't see ahead to the end of the puzzle. There's just, if you look at how many bits you're solving in this stage to go from cross to F2L, it's something like from 48 to 18. It's a lot of state. So to do this, the solvers really they have a very fast feedback loop going where they're observing constantly while they're trying to spin at an incredibly high speed, and they're definitely using a lot of memory and pattern and practice, but they're like finding micro patterns and using their muscle memory to keep moving really fast while they do that. Once they're done with those 2 layers, though, then they get into a step called orientation of the last layer, and here they get to the point where it just starts to get reasonable for a human who's really dedicated to actually memorize all the possibilities. So in the OLL stage, orientation of the last layer, good cubers, they just know stone cold the 57 different possibilities that they might see from every possible angle and exactly how to solve them. And then they finish the last step with the permutation of the last layer. This one only has 21 different cases. This step goes very, very fast because it is extremely rote. Because once you're at the end of the problem, you've narrowed the search space down so much that it's enough cases that a human can actually recognize them and know them. So you can see that using this method, you solve the puzzle in a lot less moves. Something about 55 to 60 would be typical. This method in the blue dots is usually called CFOP, C-F-O-P, because it's just an acronym for cross F2L-OL-PLL. And that's what Yihang Wang used when he got that 3.95 second solve. This is what he was doing. And the red path I still have up here, that was our beginner method, you'll remember. So I want to draw your attention to a connection back to programming, because both CFOP and beginner method, they're abstractions, right? They're abstractions in exactly the same way when we talk about using abstractions in programming, because in both cases, we're using abstractions to break up a huge problem that's very hard for us to understand into problems that we can learn to pattern match, learn to recognize, and learn to plug together. So it's a very strong analogy. All the world records for many years have used CFOP, but it is interesting that we know other methods that do use significantly fewer moves than CFOP. So the nearest method nearest competitor is a method called RU. I won't go through all the steps, but it constructs very different intermediate points. They don't make a cross, they make a couple different blocks of different colors on different sides, and it has a lot of nice properties to it. There's really eloquent arguments for why it's a great speed cubing method and should probably be fast, and yet nobody's ever used it to beat a CFOP world record. And so, personally, I think the thing that makes the dominant CFOP so fast is that it's both fast at the doing, like the movement of your hands is very ergonomic, and the seeing of what to do next is also very good in that method. And I really think that combination is something special that helps an abstraction move people along really, really fast and get into a really high degree of performance. And I think that's another lesson for us, that the abstraction that lets you do the smallest, most elegant thing is not necessarily the one, it's not necessarily going to win over one that makes seeing easier, makes seeing what to do easier. So are there undiscovered methods even better than RU? Almost certainly. And one reason we would say that is that in 2010, mathematicians finally proved that every possible state on the cube can be solved in 20 moves or less. They called this God's number, because if you had godlike powers, you could solve it in that few steps. Kind of surprising that it took till 2010 to solve that, but it is that big a search space. It took some breakthroughs in the math and 35, roughly, CPU years of processing to prove that result. And it turns out that it's actually only 1 in a billion scrambles even needs 20 moves. All the rest use less than that. So really, the green triangle here actually shows the region where optimal solves are. And you'll notice it's nowhere near where the humans are, right? It's a pretty big gap. The very fastest humans in the world are still using 300% more moves than they really need to, because it's just too hard to see the better moves. Right? I really feel I relate to this. I think this is us. Right? This is what it's like to work on software. Does it sound plausible to you that all of our abstractions are adding 300% overhead to what you could do perfectly? Right? I think so. Right? We spend our time messing about with packages and package managers and modules and linters and type checkers. And if you were smart enough, you wouldn't need any of those things. Right? But we're humans, and we do need those things. And we go much faster when we have them, even though it seems like a roundabout way. So that's the lesson I take from this stuff. So now I want to turn our attention to some of the abstractions that are hopefully helping us humans in particular go faster as we work on our Ember apps. And so this is a keynote, and keynotes usually take kind of a high-level view. But it's also, we had a weird schedule this year where there was an EmberConf only 2 months ago. We just did all that stuff. The videos are available, and I don't want to repeat things that you could just get on YouTube. I want to give you guys something new. So I wanted to do kind of a complement to those talks that does a little bit of a deeper dive into how the lower layers of the infrastructure of Ember work, how it supports the features we have and the new features that we've talked about, and how those abstractions align to be the foundations that support all the other stuff. And I hope you can take away from this a better understanding of how your apps work now, and also a better understanding of why the newer things we're working toward are good, and how you'd be able to help contribute to those as well. So let's start with a basic component example that is just written in the kind of current idioms of the current Ember stable release. We just have a component with some JavaScript. It just has an action handler that console logs something with the date in it. This is supposed to represent a JavaScript file and handlebars file that are co-located, the default way that Octane Ember apps work. So we've got a couple of import statements. We've got a component we're invoking called blue button. We've got a modifier we're invoking called on. And it's just supposed to be a pretty simple example if you've worked with Ember before. So we often use the term syntactic sugar to describe a language feature that gives you a nicer way to say something that you could have said more verbosely, or you could have said like in a stock kind of way. But the syntactic sugar is not strictly necessary, right? You could just type it out the long way, but the syntactic sugar makes things easier for humans, and in practice, it can really be critical in making a feature usable. We also use the term desugar when we want to explain going the opposite direction. Like if you start with the sugary version, the nice, pleasant human version, how does that reduce down to the more verbose, but probably like simpler, flatter, more explicit, low-level version? We call that the desugar version. So to take an example, let's talk about how our template in our example is really working. So we have this handlebars file, right? That is syntactic sugar for the thing I have on the bottom here, which is a lot like our handlebars file, but it's been wrapped in a tiny bit of JavaScript, right? This is really, if you think about it at the low level of how Ember defines and thinks about what the handlebars file is doing, this is what it's really doing, right? This precompiled template function, it's stable public API in Ember, but it's one you probably don't have to use because it's the low-level thing, right? But it's the foundation that the other stuff is just a nice layer and facade on top of. You've probably seen other synonyms for precompiled template, like import HBS from EmberScale HTML bars. There's several of those at different generations, but this one is the one that is really the stable public API that all the others you could think of as sugar for this. So that's one example of understanding both the surface level thing and what it kind of means at the lower level. And we can go down another level too. So starting from the low level public API that we just looked at, there's also an optimized implementation that you will see, right? So in terms of the code that actually gets shipped out to a browser, it's going to look more like the bottom one. This is not an example of syntactic sugar because this is now going from interface. Precompiled template is low level, but it's public API, right? It's documented, it's designed, it has a meaning, not just an implementation, to an implementation that is really, it's a detail. It's something you shouldn't have to worry about and that you actively should not target. If you actually wrote something of your own that emits this, you're likely to break in the future. You should deliberately not focus on implementation over interface, right? That's the point of having a split between interface and implementation. So the next piece of syntactic sugar I want to point out is that in our example, I said we had a co-located handlebars and JavaScript file. That itself is syntactic sugar for a JavaScript feature called setComponentTemplate. So this is our JavaScript file again, shown as a diff, where what we've inserted is the longhand way to do template co-location. Right? In this case, we're using setComponentTemplate. Again, this is low-level but stable Ember public API. It's the utility that associates the template with the JavaScript class, sticks them together in a way that they were then going to stay together forever. And once that's happened, this class, our default export from this module, it's the single JavaScript value that now represents this component, and nothing else in the system needs to know how the template gets there, if there's a template, how it's bound. It's nicely self-encapsulated in this module, and that's not a thing that was always true. Or older versions of Ember that predated template co-location did more complicated things here. This is something that already got simplified in the Octane era changes of Ember. And set the stage for some of the next stuff we're going to talk about, because being able to have components as values is critical for a bunch of the stuff that we're doing next and now. So let's look at what else is in this module and how it really works. So this module has 2 import statements. What's making these work? Like, how does that actually really work in your Ember apps today? Well, the first thing we want to say about them is that your whole module is getting converted to and I'm assuming a classic build, like stock Ember stuff for now. There's different things that would happen in an embroider app, which we can get to. Your whole module is getting converted to a format called named AMD, that's asynchronous module definition. It is the implementation Ember has used for a long, long time to package up your code, put it into one big file, and get it out to the browsers. And what's going on here is we have this define function that comes from a library called loader.js That is you can call it the loader or the AMD loader. The first argument is the name of the module we're defining, so that's coming from our file name. The second argument is the list of our dependencies. So you see Glimmer component in there, you see Luxon in there. Those are the two things we were importing. They've been converted into this. And then finally, we have a function that's going to wrap our code, and it's going to receive as arguments those things that were dependencies, right? So this is an example of one half of how the imports work today. I say one half because this is showing the consuming of them, but we still don't know where they came from. So where is Glimmer component coming from? Right. If we go searching for that, we find a define for it that looks like this. This one's in a different built file. This is in the vendor file. But why is it here? Right. In general, we need to be detectives to figure out exactly why this one's here, because there's a lot of power add-ons have over the system to insert things like this. But in this case, if the first guess is a good guess, it is coming from the Glimmer component package. We can go and find that file in there and see, okay, yes, this was very similar to what the code we wrote. This thing went through the AMD transformation. But how did it get into vendor.js? That's really just because Ember CLI hard codes it that way. That's the classic thing to do. Yeah, so all add-on, code like this that lives in some add-on goes into vendor.js. And then, so our final import was Luxon. That's just an example of a library. It's a date library. It's a reasonably nice one. And it doesn't have anything Ember specific in it. It's just a general purpose JavaScript date library. How did we get that one? Let's go searching for that. We know that we saw it in the dependency list of the AMD. So somebody must be defining it. If we go looking, we're going to find it. And this time we're going to find it in a file called chunkapp some hash.js. So this is a different case again. Why is this stuff here? This is here because Ember apps all ship now out of the box with the ability to use dependencies off NPM, powered by Ember auto import. And that's what happened here. Ember auto import looked at the source, saw an import for Luxon, saw that Luxon is a real NPM package that you're depending on. And so it sets up a bridge between kind of two worlds. We have this AMD world that's the classic thing that we've been looking at so far. And then we have an actual more ES modules-based build for all the other stuff that is not classic Ember. And Ember auto import manages the bridge between them. So in this case, you're actually seeing both halves. The define is happening so that classic Ember knows about this thing, but the Webpack require, that's actually the internals of the ES modules-driven build that happens to be using Webpack inside it as its driver, marrying those two things together. So that's a lot of steps, just to explain this one little example that I made. And that's kind of the point of this tour. It's both to give you background information that I think is useful when you start to debug a problem in your application, but also to set a kind of context for, can we do better? Can we make these abstractions simpler and cleaner? So when we talk about the AMD here, is this interface or implementation? I implied that it's just implementation, and that would be nice. But for that to be true, everything would really have to stick to the public API, which means in this case, the public API is the stuff you're supposed to type, right? It's import statements, it's ES modules, imports and exports. And if you're really doing that correctly, modules only access other modules via imports and exports, nothing else. But in a lot of Ember apps, less so in app code, but in add-ons, in many popular add-ons, people directly use the require, the define, the require.js entries, a lot of things that are very specific to the implementation, not the interface. And just as I was saying about wire format, when you use implementation and not interface, you get locked into implementation. All right, so today, AMD has effectively become interface that we have to continue to support and find migration paths off of, which is kind of the topic of a chunk of this talk. Also, like a whole point in why we're doing Embroider as the next build system for Ember is to help people get over that hump. So I'm not going to do a super deep dive into the rest of that on this talk. I don't have that much time. But let's finish the tour of our simple example and then move on to the simplified example for more of the Polaris era goals of what we want it to look like. So back in our original template, this is what it looked like, and we're using this component named blue button. And this is, of course, also a dependency. It's not an import, but there is one. There's this other component somewhere. How do we get it? So in this case, this template is what we would now call a loose mode template, which is just how all templates have been historically in Ember. But we contrast that now with a strict mode template, which is a newer thing we'll get to. In a loose mode template, the template itself is responsible for finding its dependencies. So somewhere there's a component named blue button. And in order to talk about how we get it, we have to talk about container, registry, resolver, API, and Ember. So these are layers in Ember that have been there for a very long time. When we see that in our template, that need for the component, there's going to be Ember is going to ask the container for, do you have a factory for this component? Basically, do you have a way for me to construct one of these? Now, container is the thing that exists to hold application-wide state in an Ember app. It's a useful concept. Container is a good thing to have. It's really partly why it's very straightforward to write acceptance tests in Ember, because all your state is very easy to reset and throw away. It helps with SSR as well, because all your state between different user requests is easy to reset and throw away. Container is a good abstraction. Glad we have it. In this case, the container probably doesn't have anything stateful to say about this component, so it's going to go on to the next layer, which is the registry. Registry is the place where people can register factories. We keep track of what factories we know about. Factories meaning like the class that can construct a component is an example of that. But if the registry doesn't know anything about it, which it won't when you first ask it, it's going to go to the resolver layer. Now, resolver exists because historically it was very customizable in here, and you still can customize a lot of this stuff. If you've ever seen resolver in your app.js file, this is that thing. You can, in fact, mess with it. But the simple case here that's going to happen is the resolver is going to go and find out if there is a file named, your app name / components / blue button. It's going to look for that in the AMD loader, the loader we've been talking about. So that's how it gets found. And in our example here, we'll assume it does get found. There is some component. It's in the AMD loader. Great, it renders. But then we go look in our app folder, app components, and there's no blue button component in there. So where did it come from? So how can that be, right? And so in this example, I'm going to say there's actually this add-on called my add-on, and it's providing this component to us, right? It's weird that looked like it's coming from our app, even though it was in an add-on, and this is a quirk of the infrastructure we have today. So the lookups of these things, like components, helpers, modifiers, all happen in the context of your app module namespace, right? They all look up your app / components. They don't look it up in the current add-on or current package or whatever. It's always targeting the app. What that means in practice is that to use any component in a template like this, in a loose mode template, it has to get effectively copied into the application, right? So there's this big merging process that happens. Add-ons like this one, they conventionally have 2 different directories full of files. They have an add-on directory, which is their own stuff that'll actually get defined under their name, which is what these define statements are supposed to imply next to it. And then you've got another folder, which is all the app stuff that's going to get registered under the app's name. And that's going to get merged with all the other add-ons and the app, and they kind of just fight over the namespace. The conventional thing to have in that app namespace is just a re-export, which is the little line of JavaScript I have here, which would be just, this app components blue button would just re-export the one from the add-on. But this is the pattern that add-ons have had to use all along to get their stuff in. So app tree merging is not nice, right? It complicates our build, it makes it hard to see where things are coming from. There can be conflicts between things. So it's an example of infrastructure we have now that we want to make better in the next example. And one of the last features we haven't talked about yet is that, so this add-on has a add-on components bluebutton.hps, a standalone handlebus file with no JavaScript file in the components folder. That means template-only component. That's another thing with syntactic sugar, right? Because if you don't have a JavaScript file, there is implicitly one for you. The syntactic sugar of it would be a file with this stuff in it. And this is another example of low-level abstraction, stable Ember public API that you normally don't have to see. All this is really doing is creating a new identity to hold that component so that there's something to attach the template to. And then, of course, that goes through the same set component template process we just talked about, where we're going to take that new template-only component class and associate it with our template. And now we've covered pretty much everything in our example. There's one last thing, which is the on modifier here. Where does that come from? In this case, that one's just hard-coded into Ember. It's a built-in, and you just have to know that, or you have to try to find it in the docs, even though it's a hard word to search for, right? So that's the current state. That's the kind of current state example. So let's go through an updated example using template tag, right? So This time, we've taken the same component and we've re-implemented it with template tag, which is a thing you can use now via the Ember template imports add-on. It's stable API we've committed to supporting. We're working to get it to the point where we call it recommended, where that means it's actually in all the docs and everything's been updated to work with it nicely. But it's definitely in widespread use already in certain places. I'm using it in real apps and it's very nice. One of the first things I'll say about it, I'm putting it on a slide, is that it's really nice to have a component that can go on a slide as one big statement that's self-contained and not explain, here's the JS and here's the HPS. That is a very convenient thing. And you find a lot of nice little niceties like that when you're working with them. Just like before, let's talk about how to desugar the template tag. Right? This file now is not standard JavaScript, right? This is our own extension. We would have a GJS extension on it. But we've stabilized what is the pure JavaScript representation of this thing, the desugaring of it. Right? The desugaring of it looks like this. When the template tag happens in a class body, it's understood that it's in a static block. That just gives you a place to run code in the class body. That's a standard JavaScript feature. And then we have this template function. This is a new low-level Ember API defined in the recent RFC 931 that made this low-level. And this is it's doing a similar job to what precompiled template was doing, but now there's a few critical differences. One thing is that its return value is always a component, never a bare template. It accepts this optional component argument that takes care of the job that setComponentTemplate used to do. It takes a scope so that now this template can actually see things in the JavaScript scope around it. So blue button and on have an explicit way of getting in from the outside. And the template itself is always interpreted in handlebar strict mode, which I mentioned before, and which means it will not go finding its own dependencies. It's going to use the existing system around it. So that these values coming in through the scope are the values of our component and our modifier. And so now that was the whole tour of the new thing, right? The previous version, there were a lot more steps that we had to go through. There's a couple of things that are a little more subtle. If you look at where blue button comes from, we're importing it from my add-on component's blue button. That means we sidestepped that whole app tree merging thing we just talked about. Didn't need it anymore, right? Fantastic, eject, right? When you get to the point where nothing in your code is using that stuff, we can turn all that stuff off and have a very streamlined and simplified thing. And that has big implications on being able to have the flexibility to organize your stuff the way you see fit. Because classically you had to app re-export everything, there was no such thing as a private component that you can keep inside of your package, right? But now you could. You can have one that you don't re-export to the world and you just use within your package or within one little subpart of your application. You can even have it in the same file as just a helper utility. Your helpers, components, modifiers all in the same file. Very convenient, nice to have. It's just very nice to be able to express these things purely as JavaScript. And that's the beauty of having a way to desugar custom stuff down to it's just some JavaScript expression that works anywhere in JavaScript. So one thing that didn't change between my two examples is the meanings of those imports, right? In my second example, the imports still mean go look in the AMD loader and just see what's defined there. That's the best we know about what those things are. And that's a problem because we really would like to be able to know both humans reading the code and like build systems reading the code. Where does blue button really come from? Because I would like to include exactly the right copy, only when it's needed, not when it's not, right? All that classic stuff of optimizing your builds, being able to split your builds. So being able to get a handle on that and find static meanings for all those very classically dynamic imports, that's what Embroider exists to do. The project where we're building the next generation build system for Ember. A lot of apps are already on Embroider. We've talked about it a bunch of times before, so I'm not gonna spend time on the big picture Embroider stuff other than to say like we are really chugging along. We've got more contributors than ever. We've had some wonderful support from the community, and everybody should feel free to pop into our weekly team office hours and status updates to find out what's going on and see if you want to help out, or just ask for questions if you've tried it and it didn't work. So one thing I will point out about all of this newer stuff about statically knowing how your build works and following the module graph is that even if you're not using Embroider, you probably are already building parts of your app that way. Because as an example, like if you have something like the page title helper from Ember page title in your app, this add-on shipped as a V2 add-on, which is native to Embroider. And it works in all apps, both not Embroider apps and classic build apps. And the reason it works in classic build apps is because Ember Auto Import takes care of managing that boundary for you. And so you could think of Ember Auto Import as a polyfill for the full embroider, where it's managing more and more and more of the app in the way that it actually statically manages the object graph, the module graph. And we're already moving things across that boundary, even in stock out-of-the-box apps today that have not opted into trying to get their full build done the new way with Embroider. And there's more of this is coming down the pipe very fast. So we have some work that's looking to land very soon in Ember Auto Import that's going to let you opt into controlling more things the new way rather than the old way. And so you can progressively do things the new way in your app without having a one big flag day where you switch over the whole build system. So an example of that is deciding to do your asset handling the way you would in an Embroider app, where you can just get importable URLs for assets that float around in your app's code. So the kind of horizon here is getting the very last of AMD out. So even when you're using Embroider, you still have an AMD loader present because Ember itself expects it and many add-ons try to interact with it. But we don't want to be tied to that forever, and we really want to be able to have everything running as native ES modules in the browser, because that really unlocks very nice developer experiences that we can use with stock JavaScript tooling out in the ecosystem, tooling like Vite and similar tools, where if everything runs as native ES modules, you get a very nice, delightful developer experience. So the kind of the work that we're focused on right now, I'm focused on, is landing a couple of RFCs that are going to propose some new features coming down the pipe that it would be good for folks to know about, especially add-on authors. Not going to go do a deep dive here. Don't have time for that. These are published, though, in the Ember RFC's repo. This one's a draft. It's talking about a new optional feature flag in Ember apps. It's going to opt you into these strict behaviors. Definitely, as an add-on authors especially, take a look and give us feedback. We're taking away some things that were very commonly used and trying to ship some very nice alternatives instead that are ES module safe and friendly. And I don't have time to dive into the full details of it. I'm going to go through these a little quickly. Part of that is having a static resolver. We talked about how the resolver goes to the AMD loader. It can't do that anymore if there's not AMD. And so this is going to give you an opportunity to explicitly say what set of modules is in your Ember app and give you a nice compat thing you can say to keep the compatibility. That's what that Ember compat modules import is in there. And this unlocks a couple other nice things that people might not notice they want or know they want but haven't realized it works. A thing that's kind of annoying, especially if you're trying to write a library, is to test it, you have to make a whole Ember app to test it in. And today, Ember apps really have to be a package. They need a package JSON of their own. They need some build tooling of their own. You can't just have one file that's an Ember app today, not very easily. Way back in the day, you could, and then as our build tooling got more sophisticated, we lost that capability. This begins to bring it back, because now you could explicitly just, in this one little snippet of code, make an Ember app, give it two modules, and make it run. Right? So I think this is what's going to let us not necessarily require V2 add-ons to be monorepos, and nice things like that. A nice feature that is going to be a substitute for, as we're taking away the ability to just willy-nilly crawl the AMD loader, import metaglob, nice feature for getting a handle on a lot of different modules. This is another open RFC, so check it out. I wanted to show one hypothetical example of how you might use this in a different way to think about our add-ons. So today, if you ever use Ember CLI Mirage, it has a lot of complicated infrastructure in itself to try to manage a directory called Mirage full of your code. And it has a lot of options in terms of should I include it in the build, should I turn it on, all that sort of stuff. And it also breaks under Embroider because it does classic build things that are AMD driven. I think a nicer API for that kind of stuff would be to do something like this, where apps are actually explicitly pushing modules into libraries like this. So that's an illustration of some of the stuff we're designing right now and implementing already in Embroider to make it work this way. So the goal of all of this is to get us to the point where we've got durable, standards-based apps that can run under today and tomorrow's best dev and deployment tooling. And the tomorrow part really is what comes down to having standards, right? As long as we've got really nice standards, we understand what our syntactic sugar is, what are the few low-level primitives we have, thin and clear, makes it easy for us to port those, not just to the things that we want now, but the next thing that doesn't even exist yet. So with that, I am over time, and thank you very much. Come find me and try a cube.